Hello, and welcome to today's webinar, Securing Data in Transit and at Rest. How does encryption work? Thank you for taking the time out and being here today. CCS Learning Academy is the professional training division of CCS Global Tech, a 22-year-old full-service IT consulting firm. We offer a wide range of innovative technology solutions. My name is Kajal Shalat with CCS Learning Academy, and I've been in the technology and professional training sector for the last 10 years. We also have Joshua Prado, who is CCS's Director of Veteran Recruitment, and we're your co-hosts for today's very important training. We'll be running a live Q&A at the end of the webinar, so we have enabled our Ask a Question feature, and it's on the bottom of your screen. So if you have any questions, just pop them in there. Today, we have a well-respected IT instructor who has over 30 years of extensive experience in technology for large organizations like JP Morgan Chase and Panasonic USA. And now for our presenter, Richard Brown.
Hello, everyone. How are you? My name is Richard Brown, and today's webinar is going to be about explaining the basic cryptography concepts. This is basically a part of the CompTIA Security Plus class. A little bit about myself. I'm a Microsoft certified trainer. I've delivered numerous Microsoft courses over the years, and I have various different CompTIA certifications as well. I started out as an electronics technician in the 80s, and I worked for a biomedical engineering department for a major New York hospital. Electronics was always, was my main interest since I was a young man. Then in the mid 80s, I had a chance to move into being a computer technician. I also moved to New Jersey, where this webinar is coming from, the Meadowlands area of New Jersey, worked for Panasonic. I worked for various VARs and integrators in Manhattan, as well as being a security administrator for JP Morgan Chase. For the last 15 years, I've been a Microsoft certified trainer. A lot of the courses delivered with Microsoft had technical subject matter that overlapped in the CompTIA area. And when I deliver CompTIA classes, I quite often use, some of that experience and of how overlapping concepts are delivered in a Microsoft official curriculum. So moving on, let's get going. Compare and contrast basic concepts of cryptography, explain hashing, symmetric key algorithms, asymmetric key algorithms. These are the three basic building blocks of encryption: asymmetric keys, symmetric keys, and hashing algorithms. And we'll get into, with a bit more depth, each of those three, and we'll see how they work together to encrypt data both at rest and in transit. What we're looking for with cryptography, the end result is confidentiality, integrity, and authentication. Now, from a technician's point of view, we can call that CIA: confidentiality, integrity, and authentication. From a management point of view, you could hear about the concept of the CIA triad. When you're referring to the CIA triad, then we interpret that as confidentiality, integrity, and availability, because from a management point of view, having computer systems, critical systems running consistently with high availability is a concern. Obviously, if a system goes down, then the company does not have that technology for the sake of serving their customers and making money. So confidentiality, integrity, and availability is the CIA triad. But from a technician's point of view, we think of CIA as confidentiality, integrity, and authentication, because authentication is a prerequisite before encryption. In the world of networking, authentication is also a prerequisite to authorization. And all of these topics are covered in the CompTIA Security Plus class. Non-repudiation basically means non-denial, and non-denial is achieved through authentication. Non-repudiation is often a term that's used with digital signatures. Digital signatures achieve integrity and authentication. And again, through that process of authentication via a digital certificate, non-denial that, say, the digitally signed email really came from you, because through authentication, there's non-repudiation. Okay, so weak keys and random number generation, avoid generation of weak keys, predictable elements, aid cryptanalysis. There's various different modes of block ciphers. When we say the term block cipher, we're talking about a symmetric key algorithm which encrypts blocks of 64 or 128 bits at a time. And these block ciphers have various different modes represented by the acronyms ECB, CBC, there's GCM, Galois counter mode. So there's various different modes that could be employed within a block cipher. And there's also various different algorithms that are just weak in general. For example, the WEP wireless security protocol, which was, well, we really don't use that anymore, but WEP was, if you recall, used with the 802.11b routers. And WEP used RC4 as a symmetric key algorithm. WEP was found to be easily cracked because not so much, in my opinion, as a weakness of the RC4 symmetric key algorithm, but the initialization vector, there was a small pool of numbers. The random number generator, there was a small pool of numbers in which to create constantly unique symmetric keys. So symmetric key algorithms such as DES, that would be considered weak. Triple DES is better than DES, but now we have AES, which is even better than the previous two. Moving on a little bit, data states, data at rest, in transit, in use. In use is really has more to do with data as it resides in your RAM. We're going to be focusing more on data at rest and data in transit. Data at rest, obviously, when files and folders are sitting on a hard drive. We have full disk encryption, data at rest. But full disk encryption only helps you when the computer is off. In the case of, say, Windows 10, a Windows 10 laptop, full disk encryption is implemented through Microsoft's technology called BitLocker. It then also utilizes a trusted platform module chip, which holds the cryptographic keys on a chip on the motherboard. But that full disk encryption is only helping you when the machine is off. When you turn on that machine with FDE, you will not be able to get to a login screen. Now, once you satisfy the full disk decryption and you're able to reach a login screen, or the machine is logged on, well, now we have to rely on other forms of encryption of data at rest to protect us now once the machine is up and running. In the Microsoft NTFS file system, that would be a technology called EFS, the encryption file system. And I'm going to be showing you a little diagram on how that works in just a moment. Data in transit, this could be using IPsec as we're transmitting encrypted data from one server to another server, or this could be HTTPS in a browser-based web scenario. This might be using encryption with the file transfer protocol as we're moving data in motion. Public key cryptography, algorithms such as RSA, Diffie-Hellman, ECC, various different asymmetric key algorithms. The basic idea is that they provide a private-public key pair. And the way that the private-public key works is that they are mathematically related to one another. And if the public key encrypts, only that corresponding private key can decrypt. And on the flip side, if the private key were to encrypt, then only the public key can decrypt. In my Security Plus classes, I try to emphasize to the students that when the public key encrypts and the private key decrypts, you can achieve confidentiality, integrity, and authentication. When the private key starts the encryption and then the public key decrypts, you have integrity and authentication only. So when the private key begins the encryption, in the case of a digital signature, there's no confidentiality. And as we move on in this webinar, we will we'll make that clear to you what we're speaking of. The private key must be kept secret. Yes, if your private key is compromised, then really your digital certificate should be revoked and you should get a new digital certificate with a new private-public key pair. The public key, we don't care who gets the public key, and that's why it's named as such. The public key goes out into the world. Go ahead, encrypt something with my public key and send it back to me. Only when it gets to me, where I have my private key private, am I going to be able to decrypt it and open it up and see what you encrypted with my public key from a remote location. Digital certificates. Okay, we can digitally sign email. We can digitally sign applications. We could be ensured that setup.exe, this has been digitally signed from Adobe. We can be sure that this is an Adobe program, as opposed to some other program that's trying to impersonate it as such. Drivers can be digitally signed. You may be familiar with the fact that Microsoft has become very, very conscious of digitally signed drivers, such that when you download or you install a driver into the Microsoft operating system, the operating system wants to know that it has integrity and authentication. It wants to know that it has integrity. In other words, the code is the exact same driver code as when it left Microsoft authentication. So whether it be an email or a driver, or to be ensured that we're actually dealing with the legitimate setup.exe to launch a particular vendor's application. Digital certificates, well, basically, we have a digital certificate, but unto itself, there may not be trust. With digital certificates, it's all about trust. Your individual computer can assign itself a digital certificate, a self-signed certificate. But if Workstation 12 creates a self-signed certificate, you can't pass that along to another machine, because another machine is not going to have trust in Workstation 12. I'm just going to open up Internet Explorer for a moment, just to show you that if we go to Internet Options, and then we go to content certificates, trusted root certification authorities. These are all the pre-populated commercial CAs that we have in our browser by default. And when we create an encrypted session with whatever random website, more than likely, chances are, that their digital certificate has been digitally signed by a third-party commercial CA, which then references back to who we trust in our trusted root certification authority. So it's all about trust. And a digital certificate proves the identity of the public key owner. Well, that's if it's associated with a trusted certificate authority. And when we say public key infrastructure, PKI, we're really talking about the whole umbrella of encryption. We're talking about internal domain-based CAs, commercial CAs, all of the encryption technology. So this really encompasses everything. Asymmetric keys, RSA. RSA is probably the most popular of what you see when you browse the internet. Again, I'll just bring up Bing for a second, and you see the lock sign. I'm in an HTTPS session, and this was digitally signed by Baltimore Cyber Trust Root. And when I view the certificate and I take a quick look inside under details, I can see right here the combination of SHA-256 and RSA. So this is telling me that the hashing algorithm is SHA-256, and the asymmetric key algorithm being used here to generate the private public key pair is through RSA. So pretty much almost exclusively, you'll see SHA in RSA as a combination of the hashing algorithm and the asymmetric key algorithm when you take a look at the certificates of the various different websites in which you've created an HTTPS session with. And again, this is all about, well, something. I have some further slides that explains a little bit better, or with a little bit more detail here on exactly what is going on block by block with both CIA and IA. So I'm going to reserve this explanation for some slides like right here. This is a representation of a digital signature. We have a file, and then a hashing algorithm is then applied to the file. The hashing algorithm is then going to create a hashed value. The hashed value is going to be encrypted by the private key. And the public key is going to be made available to the destination. The destination will have access to the public key, but the file itself is not encrypted. This is the reason why we don't have confidentiality with a digital signature. So at this particular point, what you see on the left, that would then be sent over to the destination, source on the left, destination on the right. It's been digitally signed. When it's received, the public key is going to be used to decrypt what the private key encrypted. If that is successful, then that is our authentication portion. Because through the public key, we can be tied, we can be referenced with the certificate authority. So if this decrypts the hashed value, and again, the digital certificate and the public key ties back to a CA, and this will yield the hashed value. The recipient, the destination, will run the hashing algorithm again and create that hashed value a second time. The two hashed values are then going to be compared against one another. If the hashed values are the same, then the file has integrity. So integrity and authentication, that is what is achieved with a digital signature. And again, from a student's point of view, or from a point of view of trying to pass the Security Plus SY0501 exam, which is a very, very hot exam right now. Security Plus boot camps and getting people Security Plus certified keeps me very, very busy. A very, very popular, in-demand certification. Of course, there's a number of different certifications, but you know, we could make the argument right now that Security Plus is right up there as far as popularity and what employers are looking for from either their existing employees or from future employees. So, moving on. A symmetric key, symmetric encryption, this is a singular key that both encrypts and decrypts. Examples of that would be DES, which is old, triple DES, a bit newer, AES, the current government standard, and these are all block ciphers. AES is probably the best that we have right now. But there's other symmetric key algorithms, you know, such as RC4, and there's various others, you know, Twofish, Blowfish, Cast 128. There's a number of other symmetric key algorithms, but I would say that probably triple DES and AES are the most popular of what we use right now. But the whole idea is that this is a singular key that both encrypts and decrypts, as opposed to the asymmetric keys in which the one key encrypts and only the other decrypts. With asymmetric keys, if the public key encrypts, the public key cannot decrypt. That's exclusively performed by the other key, the private. And if the private key encrypts, only the corresponding public is going to decrypt, which is why they're named asymmetric. That is not the behavior with a symmetric key. A singular key that both encrypts and decrypts. If I were to send you 500 megabytes of data in transit, that would be performed by the symmetric key. Symmetric keys are many, many times more efficient than asymmetric keys. If I were to try to send you the 500 megabytes exclusively with asymmetric keys, it would be much, much slower, much, much more CPU resources. It's just the designers of PKI made it such that the heavy lifting is, if you will, as I like to call it, the transferal of, say, 500 megabytes of data, that's going to be done by the symmetric key. But the symmetric key has to exist on both ends between source and destination. I have to have the symmetric key and you have to have the symmetric key. Now, one party creates this, but the problem is how do I get you the symmetric key? I create it, but now I have to get it to you in a secure manner. Well, that's where asymmetric keys come in. If you sent me your digital certificate, I would extract the public key. I would create the symmetric key. I'd encrypt it with your public key. I'd send it back to you, and then only you with your private key would be able to decrypt that. So we could sum it up by saying that asymmetric keys are used to securely establish the symmetric key between the two parties. We could think of asymmetric keys as the bodyguard, the protector of the symmetric key. And I have another example. I have two examples coming up to show you that more clearly. In the meantime, though, symmetric key algorithms basically come in two types. They come in a block cipher and a stream cipher. Now, RC4 is a stream cipher. Stream ciphers encrypt singular bit by singular bit. A block cipher is going to encrypt either mostly 64 bits or 128 bits at a time. That's kind of like the bite out of the cheeseburger, if you will. The block size. If it encrypts 128 bits at a time, that's how much it encrypts. And then there's another number, which is the key strength. For example, AES encrypts 128-bit blocks. But each of those blocks can have applied to it either 128 bits, 192 bits, or 256 bits of encryption strength. So we need to understand those two different bit sizes that are quite often associated with block ciphers and symmetric key algorithms. Again, DES, the block size is 64 bits and the key strength is 56. Triple DES is more secure than DES. It pretty much like applies DES 3 times. If I could make a strange analogy, if hitting the hammer with the nail once is DES, then the hammer hitting the nail 3 times could be the equivalent of using triple DES. AES is more secure. AES not only being more secure, but AES is faster than triple DES. It requires less CPU resources in the symmetric key encryption and decryption process. And as we mentioned, there's other block ciphers, Blowfish and Twofish are an example of that. Here's an example of encryption of data at rest. Now, I'm just going to open up my File Explorer for a moment, and I'm just going to pick out a random file on, here we go. You see these files are green? They've been encrypted. You see, if I right-click on this file and I go to Properties, this is an attribute of the NTFS file system. And then I click Advanced. You see that encrypt contents to secure data. If I take that encryption bit off, let me try that again. It should have gone away. Advanced, take it off. Okay, apply. Okay, you see now it's not green anymore. This is the encryption file system. This is encryption of data at rest, at least with the NTFS file system of Microsoft, for files and folders. Go back here, turn it back on again. And I have the choice of encrypting the file and its parent folder or just the file only. Well, I may want to do one, I may want to do the other, it depends. So this is how easily this could be implemented. You won't find this in the Windows 10 home operating system. You will find it in the Windows 10 Enterprise, and you'll also find it on Microsoft servers, because the machine that I'm doing this demonstration from is a server 2K16 data center version. So we start off with the data. The data is encrypted with the symmetric key. I colored it green to emulate what you see in File Explorer. It's encrypted. The symmetric key is appended to this data, and the symmetric key is encrypted with the public key. Now, when I want to decrypt it, I use my private key to decrypt with the public key encrypted. That's then going to yield the symmetric key. Once that is available, I use that to decrypt with the same symmetric key encrypted in the first place, and that's going to yield the data. So again, The symmetric key is being protected by the public key. Asymmetric keys protect or secure the symmetric key in both data at rest and in data in transit. Hashing algorithms, one-way encryption, their whole purpose is integrity only. Again, if I go back to a random file, here we go. Here's a file. Now, I have a little utility on here that's called click on hash. I like this little utility because it's not a separate program. It allows me to look at hashed values just from the drop-down menu here, as opposed to opening up a separate application. And here I can see either the MD5 or the SHA-1 hashed value. Here, I'll just choose MD5. And okay, it always works. And now it's got to give me a hard time. Okay, now it's got to give me a hard time. I'll come back to that and just, here we go. Here's the hashed value. Here's the hashed value. It had to think about it for a second. Here's the MD5 hashed value that program that's just generated. Now, if I were to modify the content of that file and run that hashing algorithm on it again, it would show a completely different value. Okay, so one-way encryption, integrity, run the hashing algorithm on the data. It yields a number. Run that same hashing algorithm on the data again at any point in the future. Is the number the same or is it different? If the number is the same, it has not changed. We have MD5, SHA-1. SHA-1 represents, it uses a 160-bit encryption. And then we have SHA-256, SHA-384. So there's various different hashing algorithms. NTLM is a hashing algorithm. HMAC is a hashing algorithm. And all of these different hashing algorithms we discuss in the Security Plus class. A birthday attack and collision. The concept of this, there's a thing in mathematical probability that says that in a group of 23 people, there is a 50-50 chance that two people will have the same birthday. Not born in the same year, but have the same birthday. It's a mathematical probability. So the birthday attack concept applies to hashing algorithms in that what is the probability that two completely different inputs could create the same hash value output? That is not good. That would represent that two completely different passwords could hash out to the same value, and then you could get logged onto a system with the wrong password. That's a collision. It's something that we rate hashing algorithms by. And SHA, whether it's SHA-160, SHA-256, or even more so, has a lower, well, let's just say it has a greater collision resistance than MD5. MD5 is more notorious for creating collisions. And this could be two different passwords that hash out to the same value. This could be two different documents that hash out to the same value. It's not good. It's something that we try to avoid. Back to Diffie-Hellman. Well, Diffie-Hellman is an asymmetric key algorithm. We were discussing RSA before, but again, RSA, Diffie-Hellman, ECC, elliptic curve cryptography. This is an asymmetric key algorithm where, again, it's the same relationship of private key and public key. Diffie-Hellman also introduces this concept of perfect forward secrecy, Diffie-Hellman ephemeral. And this concept, it basically means this. Normally, asymmetric keys are static. When you have a digital certificate with a given private public key pair, they are static. They stay the same over 1, 2, 3 years, the duration of the lifetime of the certificate. And then we create symmetric keys on the fly. And when we do, they're always unique. We only use them for a session. And then after that session is over, we throw away that symmetric key and we never use it again. So by nature, symmetric keys are ephemeral. They don't last very long. They're recreated over and over again. Perfect forward secrecy is the concept of, instead of asymmetric keys being static, the asymmetric keys are generated as new and different with every session. And they in turn create a symmetric key that's new and different with every session. And the advantage of that that's being displayed in here is that if one were to capture data encrypted with an ephemeral public key, and if one were to then have significant time and resources to reverse engineer what the private key is, and was successful at doing that, well, that private key is not going to do you any good anymore, because the next time you try to tap into my transmission, I'm using a completely different private public key pair. And the private key that you reverse engineered is not going to apply anymore. Now, had we done that with static keys, theoretically, you would be able to decrypt my data. So this is the whole idea behind ephemeral keys, perfect forward secrecy. And DHE, and actually there's even another one that's ephemeral, and it's ECDHE, elliptical curve Diffie-Hellman ephemeral. Key exchange. Okay, well, this is the topic of the asymmetric keys are used to securely establish the symmetric key between the two parties. In band, out of band. An example of out of band is I clear out the cookies in my browser almost religiously. And then when I log onto my bank doesn't see the cookie, and then it wants to call me on the telephone to give me a 6-digit PIN. So when it does that, it's out of band. I have a diagram coming up in which you will visually see, have a better understanding of what key exchange is. In the meantime, a digital envelope provides confidentiality, privacy. Alice encrypts the message using a secret key such as AES or Blowfish. The secret key itself is encrypted using public key. Yes. The secret key is the symmetric key, and in transit, it's being protected by the asymmetric key. And in the world of PKI, I guess we could call that a digital envelope. Fine. And I want to move on to a diagram that I created, and I bring up this diagram in all of my Security Plus classes to try to emphasize and explain these concepts. And it's right here. This is the SSL TLS process. Now, I just want to point out that SSL unto itself is really deprecated, but we keep using the term SSL. If I go to advanced and I slide all the way down, you'll see that my browser does not even use SSL version 3 anymore. I could, but that would represent a downgrade attack, potentially, if I did. So by default, it's off. We only use TLS, but we still keep saying SSL, SSL, SSL. That's fine. So all of the things that we were discussing, this can kind of, I believe, you can visually see what's going on here. right here. Here's a website, www. The website has its certificate digitally signed, let's say by some trusted root commercial CA, such as VeriSign. So they've digitally signed the web certificate. The digital certificate, now the private key is kept private. It's then given to a user because we typed in www.domain.com. And now we're in the process of creating an HTTPS session. The digital certificate has the public key. Information that was appended to this certificate when it was digitally signed was the path back to the CA to ensure that the certificate is still good. The path might designate the path to the certificate revocation list, the CRL. And if that's the case, you would download the CRIL, the certificate revocation list, which has a listing of all of the revoked public keys. And then our machine would take this public key from the digital certificate at the moment and parse through that list and look to see, is it on there? And if it is, it's been revoked. And then we know not to proceed it any further. Another technology for double checking on the validity of the certificate is to just give the public key to online certificate status protocol. And then it tells you yes or no. It tells you good or bad. It tells you proceed or don't proceed. You're not downloading a long list of bad public keys and parsing through it yourself. It's like a middleman to find out whether the certificate is still good or not. Let's assume that it is good. The next step, the client and the server are going to negotiate. We got to negotiate a symmetric key. They're going to try to negotiate the most secure symmetric key that they possibly can. Let's just say that the agreement is AES with 128 bits. Then our client machine is going to come up with a random string of bits, 128 bits long. This is going to be the seed. This is going to be the foundation of the symmetric key. It will then be encrypted by the public key and then sent over to the website. And if it was intercepted in between, whoever is in between does not have the private key to figure out what the symmetric key is. So it arrives back to the destination, who then uses its private key to release the random string of bits. So 10101010, they both know that. What has occurred here? Asymmetric keys have been used to securely establish the symmetric key between the two parties. This is key exchange. At that particular point, they both apply AES 128 bits to the random string of bits. And then they create the symmetric key. And then we, because perhaps we're buying a widget on the internet, and we use the symmetric key to encrypt our MasterCard or our Visa card. That's the secret information. So that comes over the wire, it's received. The symmetric key at the website is going to use to decrypt what the same symmetric key encrypted from the source. And then that's going to yield the Visa card, the secret information, and we're able to make the purchase on the internet. And if it's not a purchase on the internet, whatever else the packets might represent, that's going to stay confidential. Perfect forward secrecy. Maybe I got a little bit ahead of myself, but here again, let me go back to this slide one more time. We said before the symmetric key is thrown away, and with the next session, we create a brand new one that's completely different. But with regular static asymmetric keys, the private public key pair stays the same. With ephemeral keys, both the asymmetric keys and the symmetric keys are generated new with every session. And as I said before, with ephemeral keys, if somebody captures this info right here, if somebody captures that and they reverse engineer the private key, it's not going to do them any good next time, because next time is going to be a completely different ephemeral public key. So, perfect forward secrecy. And all of these things, folks, I've already given you a number of clues. I've already given you a number of clues on information that has to be, it just has to be in your immediate grasp in order to pass the Security Plus test. Okay, so over here, man in the middle, downgrade, and replay attacks. Well, let's just say this. Man in the middle, data is sent to you instead of the original destination. That could be done with ARP poisoning. In other words, the address resolution protocol is used to resolve good IP to good MAC. But when the ARP cache of the source is poisoned, then that ARP cache is going to resolve good IP to bad MAC. If that occurs when the source is sending info to the destination IP with the poisoned MAC address, it goes into the switch, and then the switch could redirect it to an attacker on your subnet, because redirection can happen in a number of different ways. Redirection can happen with the IP address. It can be done with the MAC address. So man in the middle could mean a couple of different things. It could just mean that somebody's tapping into your transmission and just passively and silently recording it, or it could mean a replay in which somebody taps into the transmission. It did not get to the destination. The data was then potentially altered. Buy was turned into sell. Yes was turned into no. And then it's manipulated and put back on the wire again. Now, there's two technologies that Security Plus points out to us to help stop these replay attacks. And those two technologies are IPsec encryption and Kerberos. The downgrade, again, using WEP, using DES, using weak protocols and ciphers, authentication protocols, using PAP, using the password authentication protocol from 40 years ago. There are still remote access technologies that accept the password authentication protocol. And if you don't know what you're doing and you select PAP as being an option, then there could be the potential of credentials going over the wire in clear text. So there's a number of different things that we have to be aware of, and I really think that CompTIA Security Plus does a good job of bringing up a wide selection of security topics for us to be aware of. And I think that's the reason why that under the 8570 regulation, so many computer technicians that are active military, so many computer technicians that work for DODs, they are required to get Security Plus certification. I'm coming toward the end here, but let me just say this to you. There is a DOD that I work with, and I visit them 5 times a year for the last 5 years just to help them get Security Plus certified. I've helped over 250 of their software engineers, their electrical engineers, their administrators, their computer techs. I've helped hundreds of them over the last 5 years because they're a very, very large DoD, and they constantly have the need for their computer professionals of whatever discipline to be Security Plus certified to meet this mandate that exists between the United States government and DoD contractors. But it's not just valuable there, it's valuable also to technicians who work in Fortune 500 companies. A Security Plus certification is a great thing to have on your resume. And it teaches you, what it teaches you allows you to then look into further courses, okay, whether it be CASP, security practitioner. This is cybersecurity analyst. CASP is a security class that maybe is a little bit more aligned to managers. Cybersecurity analyst, this is really analyzing log files, looking for attacks, looking for anomalies, looking for evidence of attackers in log files. Now, pen test, CompTIA pen test, penetration testing. Well, CompTIA Security Plus, we could make the argument covers a lot of this information, but then these classes take a slice of that information and they go into greater detail. So the point is, Security Plus, once you're proficient in Security Plus, once you have a pretty good mastery of the concepts and you pass the Security Plus test, you could then be ready for taking one of these other higher level certification tests. Penetration testing, Pen Test Plus, this is somewhat similar to EC Council's Certified Ethical Hacker. CISSP, incredibly popular, incredibly important, incredibly well respected. I assure you, if you become Security Plus certified, you will be well on your way toward taking on the CISSP certification. And then when that's on your resume, you're going to start getting noticed, because security is just becoming more and more important. And this is a great area to develop your expertise, because every network is looking, every company, every network wants security professionals. Okay, very good. So, courses offered by CCS. Courses
Perfect.
offered.
Thank you, Richard. It looks like we do have some questions from the audience as well. I know that you've gone extensively through the types of courses that we offer as well, and I'll certainly get to those in just a few minutes. So, as far as questions from the audience, I'll ask them away. And then in the audience, if you do have questions, please pop them in the Q&A chat. And if we don't get to your question by the end of this webinar, we'll be sending out a follow-up email to all registered participants. And if you want more information, certainly please email us at training@ccslearningacademy.com. I'm going to put that in the chat, as well as our LinkedIn profiles that you can follow us, and please add us on there. Would love to connect with you at some point and see if we can help you in any way in building your career path or your team's career path as well. So Richard, I've got some questions for you.
Okay.
Perfect. So in a digital signature, how does the sender generate the public key and private key?
Well, It's because you have a digital certificate in the first place. You see, with a digital certificate, you have a private public key pair. So I'll give you an example here of a digital certificate. If I type run, oops, let me say, and then I type MMC, a Microsoft Management Console, and I add a snap in, and I'm going to add a snap in for certificates for my user account. Finish. Okay. Now, if I expand on this, certificates, personal certificates, you see, look at what I have here. This is a self-signed certificate for the encryption file system. When I did the demonstration before of turning files green, when I did that before, I was able to do it because I have this certificate. And with this certificate, I have a private public key pair. You can digitally sign a document in Word. And when you go through the proper procedures and the menus in Word, I mean, just bring up Word and do a help on digital signature. And you can digitally sign a document in Word, but basically it's coming, your private public key pair, that's coming from a digital certificate. And you could have a self-assigned digital certificate, and it's completely transparent to you, and you might not even know it.
Perfect. Thanks. Great explanation there. So are there any alternatives to RSA?
Well, RSA is an asymmetric key algorithm. So basically, basically what we would be looking at is what are the other asymmetric key algorithms. We have ECC, elliptical curve cryptography. We have Diffie-Hellman. ECC is quite often an alternative for certificates on mobile devices. Mobile devices which are, battery powered. ECC is popular for those because it's more lightweight, yet its strength is still comparable. So we could just go down the list of the different asymmetric key algorithms, whether RSA, ECC, Diffie-Hellman, Diffie-Hellman ephemeral, elliptical curve, Diffie-Hellman ephemeral. There's another one, as I recall, it's not Pallier crypto system. So there's a number of different asymmetric key algorithms, but I would just have to say that, with respect to digital certificates that we examine from websites on the internet, quite often it's RSA.
Perfect. Thanks. So in case of HTTPS connections, is it symmetric or asymmetric encryption?
Well, it's a combination of both. I'll just roll this back for a second. You see, when we create this SSL TLS session, this, perhaps I should put on this list, and that once we go through this entire process, we are then at an HTTPS URL. So in other words, this is what's making HTTPS happen. So if we just quickly roll back for a second, we're using the public key from the digital certificate. We're creating a symmetric key. We're encrypting the symmetric key with the public key. We're doing the key exchange. And then when it gets over to the destination, the private key is being used to decrypt with the public key encrypted on the other side. So we could really make the argument here that the asymmetric keys were used to securely establish the symmetric key between the two parties. And then the symmetric key is going to be used for the actual work to be done. So we could make the argument here that in and going from HTTP to HTTPS that we're really employing both asymmetric keys and symmetric keys. But the transfer of the data, if we're transferring 500 megabytes and the symmetric key has been securely established on both sides, well, the asymmetric keys are out of the picture. Now the heavy lifting, I like to call it, the 500 megabyte data transfer, that would be done exclusively by the symmetric key.
Perfect. Thanks. I think we've got one more question. And again, if we don't get to your question today, we'll certainly have those answers to you as long as you've registered to this webinar. And you're more than welcome to email us for additional information. So one last question here, Richard.
Yes.
Does HTTPS encrypt data in transit?
Yes. Yes. Yeah. I'll go back to my example here. We have established an HTTPS session, and we routinely call this SSL, but again, that's just from habit. SSL is deprecated, as we're using TLS. So the data in transit could be our credit card. If we're buying something off the internet, it could be our credit card. Or this could also be used in a browser-based VPN. There are three basic VPN protocols. There's the point-to-point tunneling protocol. There's layer 2 tunneling protocol combined with IPsec. And the third one is secure sockets tunneling protocol. And that uses port 443. That is basically an HTTPS browser-based VPN connection from point A to point B. So yes, data in transit. I hope I answered the question accurately.
Perfect. Thanks so much. So thanks, Richard, for that. So when it comes to upskilling and reskilling, CCS Learning Academy is designed to be an organization's secret weapon. Our network of talented and passionate instructors, like Richard, is ready and waiting to work directly with you, your team, or your entire company. We've listed out some of our courses that we offer. And if you're new to IT or if you're a seasoned professional, we offer a range of courses, like Richard had mentioned, to really fit any of your needs. So please take a snapshot of the listed courses here. More than welcome to take a screenshot, a picture, and please get in touch with us. We're able to help you and ready to be here. So on behalf of CCS Learning Academy, Richard, we thank you for your attention to this important training and hope you enjoyed How Does Encryption Work? Stay safe. Thanks.
Thank you. Bye-bye.